Our first expert is Anastasia Belozerova, the senior expert of VisionLabs. She represents the international team in area of computer vision and machine learning. AI is called new electricity today. Everyone talks about neural networks and using them in all areas of our life, but it's not explained the way it works and how to make them solve your problems. In the next hour, Anastasia will talk about computer vision, what tasks the humanity can resolve already now, what are neural networks and how they work, how the task is set and implemented. And the most important thing is that you can write and train your own network with the help of the framework. You will need a computer, and materials will be shared in Google Colab. And of course, you will be able to write during the session and after it, without any libraries you need to install. You need just some experience on writing a code. To access additional materials during Anastasia's presentations, please scan the QR code, which will pop up on your screen. So, Anastasia, we are fully ready, and I'm sure it will be an exciting experience for our participants. Over to you, Anastasia.
Всем привет, меня зовут Настя Белозерова.
Hello everyone, I'm Anastasia Belozerova. I'm senior researcher at VisionLabs, focused on computer vision. It's the most advanced areas where you use neural networks and deep learning, and I'm happy to welcome you at the third day of AIJ conference. And technologies you will be able to see will define your choice in future. You will realize how maths is good and what's going on. And in our workshop, we will see what mathematics is behind the neural network. What are neural networks? What does it mean to train them? And one you could do at your level manually using the E-Lab. So let's begin with the concept of the neural network. So in public terrain, artificial intelligence is the most popular term, and it can do a lot of things, talk to us, generate new images, but actually artificial intelligence is a name of a generic field. Then you have machine learning, and neural networks are inside machine learning, not better, not worth a method used to analyze data. They are just different. They are better in working with information, with images, with speeches, sequences, and text. With information, a human perceives very well. And another subfield is deep learning. It's not that easy to say whether neural networks are deep or not. Actually, we call deep learning all neural networks we use for our tasks, and no one uses simple 5-layer neural networks for their purposes any longer. You will see some images I prepared for you. Today we will talk about neural networks, and we will be able to understand the main concepts. What are neurons, how to train them, and what they can do. What neural networks can do? They operate information very well, images, text information, and they can predict, memorize, reproduce knowledge they get. Neural network can learn, and you can show them data and tell them what are the right answers, and expect that the neural network will give the correct answer on similar data. So it can draw a conclusion from its learning. Neural networks cannot create algorithms for machine learning, so they can draw a picture, but it will be a repetition. A neural network cannot go outside of the boundaries of tasks set for it, although it would be interesting to use it. So neural networks can be used, well, we can tell. They can work with images very well, but what can they do with the images? They can classify the images, say, the class of an object. For instance, classify cats and dogs, a typical example. Localize objects, just use a bounding box around a class of objects we would like to find. For instance, at this photo, the neural network knows how to find human faces. It's called a detector. And at the right, there are two classes. The neural network classifies tangerines with smaller boxes and the plate with a bigger yellow box. So a detector can realize the class of an object. Also, neural networks do things like that. So we didn't only localize classes of the object. So that's a person with the chance of 99.8%, and also all objects that belong to the object. So it's like pixel-to-pixel classification. All pixels highlighted in red belong to the object which is human. So, and this is linked to a repository with networks where you have networks that can do such things. Also, the next, the neural style. The classical example would be pictures by well-known painters. And this style could be borrowed for your photo. It will not be, it will be reproduced in the style of such an artist. It's called a transfer of this style. Again, you have a link to the repository. Also, shift between domains. What's a domain? It's an area, a field, classes, and we can take pictures from like Monet pictures to photos. In one domain, you will have paintings by Monet to photos. Also, you can make horses out of zebras. That's again a transfer from two domains. You can change time of the year, summer to winter, like a change between domains. Again, you have links here for cross-domain networks. Also a demo where you can have silhouettes of cats and the neural network will color them. You can also draw shoes, bags, buildings, and the neural network will help you. It looks like creativity from the neural network, but of course it was trained. And also repositories with the description of an architecture. What else? If we would have a true dialogue, I would ask you what people are real and what people are generated by AI. So actually all people are artificial, generated by the neural network. The actual purpose of the neural network was to tell between real and unreal people. And you can find it looking at the edges of human hair, because that's the weak side of the neural network. And you have a link where you can try to have information on what's the difference. So the neural network can be used for super resolution purpose, to improve the quality of the resolution. So we had a smaller picture. We reduced it twice. We can use mathematical operations. We can restore the original image by interpolation, by cubic interpolation. Then we would get an image like this. It will be blurred, and we would lose a lot of information because we lost the picture, and we have unveil it. It's not possible to do it just by mathematical operations, but we can train the neural network to restore the image to add information lost, and again get an image that would have high resolution. So it's done for older movies. You can do them in 8K already with the help of neural networks. So again, have a link here at the bottom. So the main types of networks are convolutional, recurrent, generative, competitive, and others. You have a link here, but we have like fully connected perceptron neural networks. And what's a neuron? From which the name comes. So here you see the mathematical model of a neuron. We have some inputs that came to our neuron. They are called x1, x2, xn, and so on. We take the inputs and we weigh them using some scales. And weights of neurons are called W1, W2, Wn, and we multiply every neuron by the weights, x1 by W1, x2 by W2, and then we sum them up. So a neuron is a sum of a linear operation. So also we add like a bias called B, and we get a sum. So that's the function. So it's used for summing a linear combination of inputs. What's possible to do with such a simple thing? Why do we need to sum them up? Let's imagine we have two inputs for a neuron, x1 and x2. We can take weights, then the neuron will calculate x1 plus x2, and you can take the free member, and then it would calculate a combination x1 plus x2 minus 10. If we try to compare its value with 0 and try to activate it when it should be more than 0 and tell that it's successful, then we would get a simplest classifier. We will be able to divide a set x1 and x2 below 10 and above 10. So a neuron could help us to build up a classifier. So if the sum of two attributes is above or below 10, so this classifier can solve a simple task, and the a neuron with a dividing function can draw a line for between a surface, and we can draw a graph that would depend on the two attributes. Then the simplest neuron can draw this dividing line between the two multitudes. So here the sum of x1 and x2 would be below one threshold, and here you can have a terrain of data with highest value. So that's the simplest classifier. Also for summing a neuron, you can add another one. You can weigh and add, and we can tell between different linear combinations. Many functions that we can encode that way is just a multitude of all linear functions. It's quite small, so it doesn't end here. Then there is another function called H or sigma. What does it mean? Activation function. Activation function is nonlinear. It helps us to transform our results we got in our neuron, results of summing. And all the chain of activities is A from X, counting the linear combinations of inputs. Why nonlinear? To expand the multitude functions that use neurons could approximate the simplest sigmoid with sections pressed between 0 and 1. And so the result is 1 divided by 2. And we can put a threshold. It's interesting. If after the activation function we got the value above 0, so we can tell that objects belong to one class. If they are under 0 and the value of sigmoid is below 1/2, it would be different. It can be other types, hyperbolic tankers. So now values are between 1 and -1. So not all values would be positive. Another popular function is ReLU. So it cuts all negative values. For positive values, it makes it equal to their face value. I believe it would not be good if we cut all values below 0. You have leaky ReLU, so the input values are multiplied, so and approximated with the actual value. Okay, so let's add all the process all together. You have a value shown by arrows here. A neuron has weighs. It weighs. It means that it multiplies values corresponding to the input, 0.7, 0.6, and 1.4 in that case. Then it sums them up and adds a bias, a free member, a factor that is added to our combination. Also, let's imagine that we have input number 1. After we summed everything up, the weight inputs and the free member, we activate the neuron. We make it go through the linear function, and then it's activated. When we write the code, we don't really think that we have inputs and the neuron is weighed up. We can just understand that we have like a work in a scalaric way. We will multiply the vectors one by one, and we get a linear combination. And neural networks of every type means multiplying vectors, and there is like the multiplication of matrices of different types, and all phrases. Well, artificial intelligence you can replace by the term matrix multiplication. It would sound funny anyway. But one neuron is not that much. You can draw a straight line with a simple neuron and an activated neuron, leaving threshold for output activation. If we would use we will use many neurons and we will combine them in a network. They can form layers. What's a layer? If a neuron is in a layer, so they work in parallel. They are not linked one to the other, but every next layer would be related. So it's like multi-layer perceptron or fully connected net.
Fully connected layer or any other layer. So it's a layer that consists of neurons only. What this network looks like. Let's have a closer look at this one that we can see on the screen. We have an inbound and input layer. Input layer is just definitions that came to our network. We had 4 of them, x1, x2, x3, x4. A vector out of 4 definitions is coming in and it wants to be processed. We have the first layer, the first closed, the first hidden layer. All layers that are not input or output, they are hidden. This is just the terminology here. They are hidden inside the web, inside the network. The first hidden layer consists of 3 neurons. And what happens next? In each of the 4 entrances to the network, we're going to have 4 neurons that is located on the first hidden layer of the network. Each one of them is going to be weighed for the first element that has been defined in this neuron. Also, each one of them is going to have a bias that is going to be added. Then all the definitions and all the values of every neuron are going to be put through activation function, through nonlinearity, and they will move on to the next fully connected layer and to the next hidden layer that consists of 3 neurons as well. Every successive neuron will receive the result of work of the previous neuron. So from each of the outputs that we have as a result of the first hidden layer. So each is connected to each. We have a dense web here. Each must be connected with each successively. And each one has their own bias, and they're going to go through nonlinearity, and they will move on to the last output layer. Output layer, this is an important thing here. For classification tasks that we're discussing right now, for perceptron, the number of neurons in the last layer must be the same as the number of classes by which we're going to classify our initial information. Let's imagine that this was a vector image. And in the end, in the output, we want to classify it to 2 classes. This is why in the output, we can put this layer with a length of 2. There are going to be only 2 neurons. Length is 2. What's going to be the type of this image? The neuron that will have a stronger activation. So the neuron is going to have a higher value. This one is going to be activated. If it was the first neuron, it was responsible for the class of cats, for instance, then we have a cat. If it was the second neuron, it was responsible for doggies, and it's going to be a doggy. Every neuron is responsible for the type of image, and we predefine it in advance. And depending on the value in the output, the higher the value, this is the first one. So we can classify it this way. In the end, we're going to use a non-regular activation function. Or you might skip it, actually. You might use just the maximum value. It will not be interpreted, and then we'll take maximum, and we'll say this is a maximum value, and it means that this is the image. This is the type of the image. We can add another function that will convert all the output values into probabilities of types. And as a result, all the values in the end will equal to 1. And we will see what's going to be the distribution of probability among types. This function is called softmax, and most often is taken as activation function in the output. Inside, where we can have one function such as reload, many like reload function because they're very high performing. And in the output, we don't like it because why do we need to bring everything down to 1? We don't need it. Here we need softmax to convert probabilities of types distribution, or we can use a sigma curve so if we want the values to be somewhere between 0 and 1 strictly. This is how we can do classification. So how can we do this linear layer when we have a lot of such layers? Not 1, not 2, but many. We should do reorganization. We have a vector that corresponds to every weight that has a parameter inside, that has an x inside, and we can bring it together, all the vectors and as a result, we will receive a matrix of these ways. The incoming x will be multiplied by matrix of ways and will multiply it by 1 bias. And every neuron has its own bias, and they're brought together afterwards. Every neuron in the web has 2 parameters: weight matrix for every weight and vector of biases. These are learning parameters. They can be trained. Depending on the B vector and bias vectors, we can adjust the web response to different inputs or outputs. They can be trained, and we train our neural network in such a way so that they respond to cats and other images in the right way. This is what it means to train the web. We train it the right way. Here you can see a GIF, and it demonstrates how it works. And here you can see a link to a video. You can hit the link and you will have more details about how it works. And here you can see how full-scale networks work here. This is an inbound layer, and this vector is sent to neurons of the first layer, and we see the whole web here. We see that some neurons got activated stronger, some neurons got activated not that strong, and they are transmitting these values further to the next layer. They calculate their weighted amounts there, and they go through activation again, and then they go to the output layer. Here we see which neuron get activated, the highest value, and this is the type of image that is in the output. Now let's see what it looks like at the output. We're going to code it with the help of PyTorch. PyTorch is the best framework for neural networks. And we will need linear layers and nonlinear layers. We're going to use reloop. So what are we going to do? First, we're going to import the torch itself. It's called PyTorch, and this is torch for Python. We're going to code on Python. We just import the library, and from there we import separately an NN level. This is a library that has all layers that had been written on Torch previously, and they can assemble a neural network. Let's import it all. Let's try to do it. Let's disable warnings. We don't like warnings. And let's add the libraries. Okay, we've added them. What do we do next? With the help of Torch, we make sure that the video card is available. Collab provides an opportunity to use video cards. Video card is a great resource to do matrix multiplication, and we know that artificial intelligence is actually matrix multiplication. We'll need to do a lot of that. Let's do it. Let's use it. Neural network is going to consist of these layers, and linears. You can see the link over here on the top. So what do we need for linear levels? The number of inputs, number of x1s or xn's that will enter the layers. This number, this quantity corresponds to the number of weights for every layer. Out features are the neurons, the number of neurons per every layer. We need to have 1024 neurons or any other number, 512, for instance, neurons on this layer. But in the input, we're going to have 4096 elements, and every neuron is going to have these number of outputs. It cannot be changed further. This is the linear level. We will have a vector that will consist of biases, and it works by default. Bias equals true. And there's going to be another vector of length 512 that will have trainable learning biases. After we do it, then we launch the ReLU. This is activation function. Then we type in another linear layer. We want to have 3 of them, for instance. How many inputs are we going to have here? On the first layer, we had 512 neurons. Every neuron has its amount, goes through nonlinearity and moves on. In the next layer has no choice. It must welcome all these 512 values from the first layer. So these are the inputs for every layer. And how many neurons each? Up to you, 128, for instance, 100 or 50. It's really up to you. Then the same thing, nonlinearity, and the last layer that we're going to use here, we're going to have the same amount of inputs. So the number of inputs, it must be the same as the number of outputs from the previous layer. And in the output, we're going to have as many neurons as classes. For instance, 2 classes. We have just 2 classes. Let's have a look at the web. So these layers are also represented as NN sequential. NN sequential does the following. Every layer is going to work successively, only one after another. They have a strict sequence. It's a directed graph, so distribution of knowledge happens in one direction only from beginning to end only, and layers follow one another strictly. In sequential, we fix this order. Okay, we see that actually we have 5 layers from 0 to 4. Let's see what is going on with the first layer that has index 1. The first layer is ReLU. Okay. Does it have any parameters or any properties? Let's type in state dict. It is a list of vocabulary for this line. The ReLU is just an automatic operation that just converts our outputs. And what if we look at the linear? It has weights, it has learning parameters. These are the ones that we want to see here. The weights consist of 2 parts, weights and bias vector. Let's have a look at the size of bias vector, at the shape of bias vector. The shape is going to be 50. Reasonable, makes sense, because here we had 50 neurons, and every neuron has its one bias, and the length is 50. Okay. We can code a different way. This is the simplest option. Any person can do it, anyone. It's really primitive. But decent people, researchers, actually type in class of the network, like this one. For instance, let's call it EasyNet for advanced students. What does it mean? What does it mean to type in a class? We inherit inan module, and we're going to use the methods that had been coded in there. What do we need when we type in the class of the network? We need to initialize it. We need to write the attributes. We need to write all the layers here. We need to indicate all of them. Let's have this linear level with this size of input and this number of output. The second layer with this input and output. This is the third layer of inputs and outputs. Or we might skip the third and the fourth layers. Let's delete the fourth layer. Let's use only 3 layers, for instance. And let's fix the activation function that we're going to use between the layers. Here we have initiated this. This is the set of layers that we're going to use in our network. The network also needs a forward method to be coded. Forward method is the principle that is going to guide the entrance in the input. What's going to happen with the X that enters the network? It must be flat, so we must extend the vector. And the last size must be the same as the number of inputs on the first layer. Then this flat input goes through the first linear level, and it gets converted somehow, and we receive some amounts that neurons calculated. Then we should go through nonlinearity. The same thing happens on the next layers. It goes through the second layer, nonlinearity again. The third layer, we decided that it's the last layer. This is why these 2 last transactions might be taken away from here. X is going through this algorithm. First, it's flat. Then it goes layer by layer. And in the output, we're going to receive a reorganized converted X, upgraded X. Let's try to create this web. When we type it in here, it doesn't look as clear as the first one with the help of container and then sequential. Here in reprint, we can define only attributes of class that we wrote here in an initialization. And based on these attributes, we can't understand what's happening inside this network. We need to look at the forward. X go through linear level, then it gets activated, then it goes through the next level, so on and so forth. This method is more advanced, actually. It's when you have large networks, it's not easy to use it, but when we have a simple task, then it's easy to use it. Now we want to train the network. We want to train the neural network. It means that we have some data to train it on. For classification, there's going to be some images. We're going to have images and labels on them. Training the neural network. It means a fine-tuning vector of biases and weights, matrix of weights. We want to shape it in such a way that the network gives us right answers all the time and makes as few mistakes as possible and chooses the right images. It classifies the right images in the right way. How do we formalize this request? There's a function of losses. Function of losses will depend on inputs that enter the network, on the outputs that leave the network, so on distribution of values from the output neurons, and on classes of neurons that belong to this picture. Losses function is going to depend on the label and on neurons' inputs and outputs on every picture, on every image, depending on the label. We want this losses function on the training data set to be small. We want to gradually reduce it so that we have fewer losses. Let us calculate this function for every element of our selection, and let's make it average. In this case, we're going to receive average losses. Neural networks with these weights is going to have it, and we will have to tolerate these losses. We want to minimize the losses that we'll have to tolerate further. If our function of neural network gives the right answer, if it chooses images correctly, then losses will equal to 0. If it's not equal, if it doesn't equal 0, then the loss is gonna have some value, and the average losses must be as small as possible. Let's have this curve of losses curve. This is what it looks like. It looks like a parabolic curve, and on x-axis, we have parameters of network. In this case, we presume that we begin with an initial value. We will have an algorithm working from this initial value. This is the first violet dot, and step by step, gradually, we optimize weights of our algorithm, and we will reach the minimum. We will have minimal losses. In this case, our neural network is going to make as few mistakes as possible, as few errors as possible. And it's good. It means that it has learned how to do the algorithm. This is our goal. This is where we need to get. How do we do it? We do it with the help of stochastic descent. We use gradient. Briefly, what it happens, gradient is a vector that indicates the fastest growth of function. For instance, from this point, it would show us gradient up. It would show the direction upwards. But we don't need to go upwards because we want to reduce losses. This is why we need to use anti-gradient. It will help us reduce the number of errors. We want to get there. This is our direction, downward towards the minimum losses. If we count gradient of our losses curve on all the weights that we have in our neural network, then we'll be able to calculate this gradient, and we will reduce these weights in the direction of anti-gradient. So we will be making these steps. We will gradually reduce weights, not actually reduce, we will change the weights, not necessarily reduce. That will drive the prediction of the neural network, and that will drive the losses for the network at every input level. We will do it iteratively towards anti-gradient. This is the way you can put it into equation. And there's another parameter, and we multiply this anti-gradient by learning curve, or a step by which we're moving. So it will define the pace with which we're going to move. So what does it look like on a picture? For instance, we have this surface. This is a loss function. It never looks that beautiful, but let's assume that it looks this way in this case. Right now we're somewhere in the green, and we need to go to the bottom and minimize losses. With the help of gradient descent, we will be able to iteratively reduce the weights and get to the minimum. It's very difficult to calculate it. We have a complex function. We have a lot of layers, and they are one on top of another. And now we need to calculate the derivative on all the components. It's very difficult, but it's actually possible. This can be done with the help of backpropagation. We can calculate it this way, but every subsequent layer of neural network actually just reorganizes it. It's just a complex function, a function from the input, from the very first image that enters the neural network, from the very beginning. Gradually, we put the derivative, and we will be able to calculate all the derivatives from the beginning till the end. So we'll be able to calculate the gradient of our function depending on the weight from the first one to the next one, from the first layer to the next layer. And we will be moving backwards. In the forward method, we move from beginning to end, but in backward method, we move from back to beginning. we gradually reverse the function. Here you can have a look at the video. You can have more details here. Here's the link on the screen.
So we calculated the gradient of our function for a certain value, and one can take a step on the anti-gradient. If we do it to every element of our sampling, then the movement would be slow. So normally a set of images called batch is used, and it goes through the network simultaneously, used to calculate the average gradient. So you take the movement of gradient descent, and the weights in the network are updated. Also, there is epoch, a period of time which took our network to see every image. So this is how the process of learning is structured. There is a sequence, so we see the loss, and we update the weights batch by batch, and this is done for every images combined in a batch until we reach the end. So when we will look at all images, it would be one epoch for our network. Let's then formalize it. Train function. In comments, you see what's going on, and you have to pay attention that you iterate epoch by epoch, and inside the epoch you iterate batch by batch. You have inputs and labels for all our images, and you use some optimizer. The method of gradient descent optimizing weights of our network. So you have outputs, you have predictions for neurons with maximum values. The characteristics, we read the loss for a number of inputs and outputs, and we do the backward, the input for calculating the gradient, and updating ways step by step with the help of our optimizer. So this is what's going on during the training for every batch. We got the prediction values for a network, we read the loss, and we update ways values. So we do the backward. Also, as for evaluation, you have the same process, and you can track the process. We just don't use optimizers to take some steps. We just update ways. We test it, and now we can predict values, what loss values we will get. Okay, let's try to prepare data. I took a data set of Simpsons characters you probably know well. I tried to simplify it and made it, neural networks are used to resolve some social networks. So let's try to classify Simpsons. My data are available here at Google Disk. Have the disk, please. You need to attach your Google Disk here. So I select my account to edit, and type in the authorization code. We will have the Google Disk, and you can work with the files as if it were in a folder on your laptop. Let's see what we get. If we see the data, yes, the archive with the data at the Google Disk, Simpson data. So let's let's unzip the archive and put them into a folder nearby. So we have Simpson data, and we have a train and test folders. So how many pictures we have here? 12,768 for training and 831 for the test. That's the description, the annotation, with the names of pictures and labels that correspond to them. How do you work with the data? You need to combine them in a data set. A data set needs to know how to read the picture, do some transformation, and then send the picture for the output and give the correct name. It all helps here with Simpsons. It takes Panda set train a certain image, takes the path to the picture, transforms it, does the transformation we need, and then it sends it to the target, adding the labels of the class. What will be the transformation? Let's do the resize. Let's make them square, 64 to 64. Then we need to transform them to tensor, because neural networks only work with tensors, and their weights are tensors. And then we will continue normalizing them. With normalized data, it's easier for a neural network to work. And so when data are in pictures, and it makes it easier for a neural network to work with them. Yeah, so the same train and test. We need loaders for train and test. What do? A loader takes a picture from data sets defined before and combines them in batches of a certain size. So we set 64. Then you need a shuffle, just to shuffle pictures and to have different batches, epoch by epoch. Otherwise, it would be simple if the picture would see the same batches every time. So it would be harder for it to get to optimal values. Okay, let's take the next element from our train loader. Let's take target pictures and see what type of data we have. Data we transform like this. So this is the way our images look like. They had a certain sizing. Now they are squares of 64 to 64. So batches are normalized and they will go to the network. They are concentrated. So on some pictures, faces are in the middle of the frame, so then the network will cope with them. So we trained our network. Let's try to test it again. We have an advanced network. What will be the input? We will get pictures of 64 to 64 to 3. That would be the input vector. That will go to the very first layer of our network. We also have a parameter, the number of classes. So we set 18 because we know that for this data set we have 18 characters. So at the output you have 18 neurons. Then we set it to a video card. All neurons should be either on GPU GPU device. So GPUs are good for optimal calculation. So for matrix multiplication to accelerate calculations. Then we have a train loader. It's like above, and I give you it as an example for you to see what you need for that. You need to send train sets for train loaders. It will take pictures and combine them in batches, preset batches. You also set the number of workers. You shuffle. You don't need it for the test, but you do it for training. You need to know the final metrics with accuracy. You will drop last pictures, which are not united in one batch because the size can not be applicable for the size of batch 64 to 64. So the last ones, which are not in a straight batch, should be dropped. They could have like some noisy value for our gradient. So it makes sense to drop pictures which are not applicable. What I did next, I set the optimization method, the SGD method, stochastic gradient descent. And for our optimizer, for our meta optimization, we need to set parameters. What does it mean? So values, it can change and it will use to calculate our gradient vector. So in this case, it's applicable to the entire network. It's a net of 3 layers, and all parameters of weights and biases we give them to the optimizer for it to change the value. Also, we set LR. The step we would multiply our gradient value, and we will use to move it. It's a very important parameter for training. Well, it makes sense to take the highest value to get to the minimum with the loss functions. If we take a very high layer, then at this simple graph, we can step very proactively to the minimum, and then we may start to grow. We will be above this local minimum because the speed was very high. So LR is not, it should start from 100th, but for other optimization methods, well, it can be 1000th when it's a really big data set. On ImageNet, quite often you start to train networks from 1/10th, but anyway, you need to reduce this grade. Let's have a look. We trained our network in 5 epochs. So at the first epoch, our percentage was 0.5 and the train loss was 2.2. It was when the network first saw our pictures and tried to update the weights. Still, the test accuracy was 50%. It's cool. On the second epoch, the train loss went down 1.6 with less errors. So everything's well. We are descending, following our method of gradient descent. The accuracy now 53.9%, and it followed with all with every next epoch. Train loss was going down and accuracy was going up. Now it's 75.7%. So as for the learning rate, let's decrease it in 2 times. When you will have all the materials, you can use it with the same learning rate and see if you can match this minimum of 75%. Or maybe we could go down to the really optimal minimum and the accuracy will grow. Okay, so let's take 5 thousandths as our learning rate, and let's see what will go on. I forgot to say that we had the cross entropy, the loss function. It's not, this loss function is not that easy, but it's typical for multi-class classification. It's the most popular. There are a lot of loss functions possible. We wanted it to be differentiated because we need to calculate the derivatives for all parameters of our network. We need to calculate the gradient, weights and biases, and we need to know to activate it. That's why we need it differentiated. What's going on now? We have the next 5 epochs with lower learning rates, with an optimizer for the stochastic gradient descent. So the progress is going on because our network is already trained to a certain degree. We keep optimizing the parameters, but we decreased the learning grade. So our steps towards anti-gradient are less. So it's fine-tuning. Look, so last time we stopped at 75% of accuracy, but now steps are smaller. And in classification for 18 classes, it's 86.3%. It's quite good, yeah, because the loss rate keeps going lower and accuracy keeps growing. If we were in a situation when we kept the minimum, if we would skip the loss minimum, then it would mean that our selection was not quite correct. And you need to catch the moment, and again, losses started to grow, and accuracy is not growing anymore. It's not quite well. So you need to be more cautious when choosing a strategy for the learning rate or using another optimization method. There is an add-on, another popular method inside the gradient rate. Here, we are not just based on gradient rate purely. We use momentum. What's a momentum? A momentum is like an add-on, meaning inertia. If we are falling down into a hole, we need to keep the rate just to skip those minimum rates, because we want to arrive at the point of the global minimum of our loss functions. We're not interested in global because we can get stuck and in our learning. What's a global and a local minimum? So this is the surface. It doesn't have any minimum. It's like a mountain. It's a hilly terrain. There are many minimums, and we can get stuck in a local minimum. The result would be still okay, but not that good. And of course, we would like to skip those local minimums. After 5 epochs, we arrived 91% after 10 epochs in just 8 minutes. Not that bad for such a task. Let's try to visualize pictures. There is a separate function. So we have 71 pictures out of 800 where there were mistakes. Where it happened, like true class is Homer Simpson. And the predicted class is Abraham Grandpa Simpson. They are quite similar, and the situation is typical for Grandpa Simpson. And the score is quite high. And I also used softmax for the function. So the probability saying that this is Grandpa is quite high. Maybe it's a difficult case. Anyway, let's continue. So Homer is confused for Moya. Krusty is identified as Milhouse because Milhouse has blue hair as well, and the confusion is easy, but the chance of probability is not that high. So this case is difficult for the network. It should be trained more. The practice of seeing is quite good. So you can see that the network misses some data. You need to add more pictures, and you can see that all characters are quite far away, or on the contrary, so they are quite close. So maybe at the training stage didn't have any images where the Krusty was shown, and the network just couldn't be trained. So you need to know the difference between the train and test data set to smoothen the difference. You need to visualize all the pictures and try to see some logic. So March and Homer, a very strange mistake, but the score is very low, so it means that the picture is not clear for the network. So point 3, the network doesn't understand what neuron should be activated for a picture of that class. Okay, let's move towards the conclusion. What should be the takeaways from this workshop? Don't worry if you don't understand anything, so because many of you will still have mathematical analysis, optimization methods, probability theory, linear algebra, and so on. It's good to know that all to really know what's going on in neural network, what happens when you train neural networks, not just pressing train and test button. So it's not the approach of a researcher. So if you don't understand it, it's normal. Just try to understand if it's interesting for you, if you are ready to do the programming, if you are interested in mathematics. If it's your case, then I left a number of links for you for some tutorials on PyTorch from the University of Amsterdam. They are in public domain, and please use the links, read the articles, watch the video I recommend to you, and try to have more experiments with the data about Simpsons. Try to change the learning rate. We tried 2 values. You can have more steps, or you can use a different initialization, use a different optimizer. You can rotate data by 15 or 20 degrees and see what would be the results with this data set. If you arrive at 95%, it will be well done. You would be great guys. Actually, what we saw today, it's a very simple data set. We no longer use it like this. We no longer use convolutions, convolutional networks, but convolutions is a different story, and we will have another discussion on that, or maybe you find out how to work with them yourselves. Good luck.